series. When your heart starts to flutter and you can hardly.
Integrated rate laws. Now, if you don't have a background on rate laws, I suggest you learn about it first in order to understand this lesson. The rate law relates the rate and the concentrations of reactants. We can use an integrated rate law to determine the amount of reactant or product present after a period of time, or to estimate the time required for a reaction to proceed to a certain extent. For example, an integrated rate law is used to determine the length of time a radioactive material must be stored for its radioactivity to decay to a safe level. Rate laws tell us the rate or concentration at a given instant, allowing us to answer questions such as how fast is the reaction proceeding at the moment Y moles per liter of A are mixed with Z moles per liter of B, and what is the concentration of B when the concentration of A is X moles per liter. For integrated rate laws, we answer questions such as how long will it take to use up X moles per liter of A, and what is the concentration of A after Y minutes of reaction. So in integrated rate laws, we include time as a variable. The equations are given in this slide for the zero order, for the first order, and for the second order. This A here is the final concentration of the reactant. Rate constant is the K, and T is time. While A naught, this is read as A naught, is the initial concentration of A. So now we'll look onto this problem. You just have to plug in the values, isolate the variable you have to find. Like for this example, you have to know time because it asks for the length of time. So you only have to look for K, A naught, and A. So K is given, which is 9.2 times 10 raised to the negative 3. How about A naught and A? Well, it says here 80% will decompose, which means that 20% will remain, which leads us to a value of 0.2x and A naught being x. So with this, we can cancel x and solve for the variable t, which is equal to 170 seconds. Now, at the bottom here, we can see the equation translated to a slope-intercept. So this is useful if you want to graph given data values, like you're given the natural logarithm of a as the y variable and time as the variable in the x-axis. So you can plot that, and you should be getting a negative slope, which looks something like this. So for the second, we'll just approach this the same way. We find the equation appropriate for this, which is the second order equation, which is this, and we just plug in values and isolate the variable that we want to look for. So in here, it is given that the k, or the rate constant, is 5.76 times 10 raised to the negative 2. The initial concentration, or A naught, is 0.2 m. The time of 10 minutes. So we just plug in those values, and we should arrive at 1.79 times 10 raised to the negative 1 molarity. And this should give us a positive slope if you want to graph it using time as the variable in the x-axis and 1 over concentration of A as the variable in the y-axis. So lastly, for the zero order, this is the equation, and as we can see, we'll get a negative slope which looks something like this. So that's how simple integrated rate law. So that's how simple the topic is. Just have to know the 3 equations and just play with the values. So I hope you understood the lesson, and thank you for listening.